This is the second lecture on advances in large language models. We talked about logistics, and I tried to give you an overview of what has been happening in the space of LLM since last 6-7 years. It's very difficult to capture in one day, but I kind of tried to give you an overview of what we have seen. And every day new things are coming in. It's an extremely exciting area, right? Not for research but also for development, right? I will try to give you recent updates on LLMs as a breaking news in my lectures, right? And hopefully we'll be able to kind of try to see the development and try to cover those development in this course. So in the last class I told you that there is no prerequisite as such, but we will not teach NLP and deep learning in this specific course. I offered this course last year also, but last year we started with basics of NLP and also covered deep learning little bit, right? But this year we are not going to cover NLP and deep learning at all, right? So the prerequisite for this course is essentially you need to go through first 10-12 lectures of the last year's offerings, right? I hope all of you have already gone through the lecture materials, and if you have already gone through the lecture materials, you should already know about, let's say, language model, what language model is, right? CNN, RNN types models for language modeling, and then different types of embedding techniques like what to fake, right, glove and stuff like that, right? We are not going to cover all these things, by the way, but the plan is that, see, in today's lecture I will talk about language model and neural language model in a very, very, very high level, right? 100,000 feet above the sea level, right? So I'll make it very high level so that you have some ideas about it. And then next class we will start from transformer, right? So we'll discuss transformer, then different so one class will discuss transformer, next class we'll discuss different pre-training techniques, and then instruction fine-tuning and preference optimization, right? So in next 3-4 lectures we will finish till preference optimization, right? Basic preference optimization, and then so let's say in around 14th of August or 15th of August we will start from advances in preference optimization, different RLHF kind of techniques, right? PPO, DPO and stuff like that, GRPO and so on. Okay, so as I mentioned, today again we'll try to make it very high level, very, very quickly go through some of the basics. Language model, as I mentioned last class, it is basically probability distribution over a sequence of tokens. Sequence of tokens can be words, can be characters, images and so on, right? And if you model it using let's say if you want to predict the probability of this, measure the probability of the sequence, I like pizza with lots of dash, right? Or lots of, let's say, lots of cheese, right? If your language model is good, it should be able to say that the next word is going to be cheese, not corn, for example, or not it should not be tree, right? So probability of a sequence of tokens W1, W2, ... Wn can be calculated using conditional probabilities, right? You can use chain rules, and this can be written as P of W1 times P of W2 given W1 times P of W3 given W1, W2 ... P of Wn given W1 ... Wn minus 1. So each of these components except this one, all other components, you can also think of this as conditional probabilities but in a different way. So all these components are conditional probabilities, right? This is also conditional probability. You can write it in this way: P of W1 given start, where start is a marker indicating the beginning of a sentence, so sequence, right? So now how do you calculate these conditional probabilities? if you go back to the statistical language modeling part, what we can do, we can simply count based method. So probability of, let's say, going IM is probability of, it is basically count of IM going by count of IM, right? And you have access to a huge corpus. You basically look at the number of times the sequence IM appears and how many times the word going follows after IM, right? So, and in this way you can estimate it. The problem here is that if you have larger sequence, so let's say this one, right? P of Wn given W1, W2 dot 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 Wn minus 1. Let's say, so this is called context. If a context length is very long, you may end up getting a count of 0, right? You will hardly see an occurrence of a sequence of tokens, right? And if one count is 0, if a numerator or the denominator is 0, then you will have problem, right? Because ultimately you are multiplying probabilities. If one of the probabilities is 0, the entire sequence will be 0, right? So what we do, we make assumptions, and we make we basically use Markov's assumption, first order Markov process, second order Markov process, and it says that, I mean, you can think of these tokens I am going as different states, right? And then you make assumptions. First order Markov assumption says that your movement from one state to another state is dependent on your current state, right? Zeroth order Markov assumption says that it is not dependent on any state, right? And so on and so forth. Similarly, you can think of these words as states, and then you can say that, okay, I will assume first order Markov assumption or second order Markov assumption, right? And then all this long context, right, can be essentially reduced to a limited sequence of tokens. Let's say, for example, your sequence length is, so you are always going to consider, let's say, sequence length of 2, context length of 2, right? So then this probability is going to be P of W1 times P of W2 given W1 times P of W3 given W1 W2. So far, look, the context length is less than equals to 2. It is okay, right? Now the next one is going to be W4 given, ideally this should have been W1, W2, W3, but because of this assumption that the context length will never be less than, greater than 2, I will basically chop off W1, and this will be P of W4 given W2, W3, right? And so on and so forth. The last one will be P of Wn given Wn minus 2, Wn minus 1. And then you can use chain rule and all these assumptions, and you can easily calculate the probability. Okay, so the Markov assumption that I talked earlier, right? In NLP, this is called n-gram assumption, right? N-gram assumption. And the idea is that, let's say, and n can be 1. If n is 1, this is called unigram. If n is 2, this is called bigram, and so on and so forth, right? So if the context length is 1, then it's called bigram. Okay, if the context length is 2, it's called trigram. So bigram means 2 words, right? Let's say I am, it's a bigram, right? And when we measure the probability, I will say probability of m given I. The context length is 1, and I am considering 2 words at a time. That's why it's called bigram. Similarly, trigram, fourgram, and so on, right? So you see that n-gram, an n-gram language model is n-1 order Markov process. Why? Unigram Markov. So unigram language model is 0th order Markov process. Bigram language model is first order Markov process, right? Okay. So the problem with n-gram model is that it is not able to capture long range dependencies. Let's say this is an example. The project which he had been working on for months was finally approved by the committee. So if, let's say, your task is to predict the word here at this position, right, it is impossible for a language model to look back to the word project and guess the next word. Why? Because if you do, if you want to do that, you have to take care of, you have to consider the entire sequence of words as context, right? And we already said that if you increase the length of the context, you may end up getting a probability of 0. So you hardly consider the last word or the last 2 words or last 3 words and so on and so forth. So long range dependency is very difficult to capture using n-gram, right? So therefore we will see so statistical language model. So this is statistical language model is not not an advanced solution for language modeling objective, right? We will actually go towards neural language model. Okay, but before that, let us try to understand how we evaluate a language model. Can somebody tell me how we evaluate a language model? So the objective is to predict the next word, right? So how do we evaluate it? So one way, so there are 2 ways to evaluate a language model. One is through extrinsic evaluation, right? In extrinsic evaluation, you take a task. Let's say the task is machine translation, translating one language to another language, right? So task, you apply language model 1, right? You get some accuracy 1. You apply language model 2, you get accuracy A2, right? So if A2 is greater than A1, then L2 is better than L1, right? This is called task based evaluation or extrinsic evaluation. The problem with task based evaluation is that you are dependent on the task, right? And nobody knows what is the ground truth task that we should consider, right? Nobody knows whether machine translation is the best task to consider, or summarization is a task to consider, or filling the blanks is a task to consider, and so on, right? You can also think of tasks like let's say we have all seen this GRE TOEFL types questions, right? Synonymous word, antonym, right? Synonym, antonym types. You can also use language model to predict those things. But this is task dependent, which has problem. Therefore, people came up with this idea called perplexity, right? Perplexity is intrinsic metric, task independent metric. What is perplexity? Very simple. Perplexity is the probability you measure the probability of a sequence W1, W2, Wn, right? And you take the nth root of that, right? And 1 by that part. Okay. Now, if you go back to my previous lecture, you see that perplexity has a very nice correlation with entropy, right? But here it is not required, right? But you just need to remember that perplexity is a measure which we use to evaluate the performance of a language model, right? Now how do we measure this? So higher the perplexity, higher the probability, lower the perplexity, right? So if a model's perplexity is low, the model is better. Okay, so we always want to minimize perplexity, right? And how do we measure this probability? So this probability is measured using your language model, right? Let's say your language model is a bigram language model. So this is going to be 1 by nth root of right? Wn given wn minus 1. This is your bigram language model, right? If it is trigram language model, then this would be different, right? And then you see for which language model your perplexity is minimum, and that's going to be your best language model. Okay, clear? All right, let's move on to neural language model, right? So in neural language model, the first assumption is that you so the input to the neural network, right? A simple neural network, like let's say a feed forward network. The input to the feed forward network is the embedding. What is embedding? Embedding is a vector representation of a word. If you have not gone through the lecture, please go through this word to vec, right? I will not cover this, or glove, or fast text. So these are some of the embedding static embedding methods that we generally use to obtain the vector representation of a word. So far in n-gram language model, I have never mentioned about embedding, right? But now we need embedding because in the neural network, the input will be numbers. We can't feed a text into neural network, right? So your input will be a number, and the numbers basically in our case are vectors. Okay. So let's say again the same objective, next word prediction, and this is the sentence. The sentence is, as the proctors, is not clear here, as the proctor started the clock, the students opened their dash. Okay, so and the model that we are going to discuss is called fixed window language model, fixed window neural language model, where you first need to discuss or decide the context of the sentence that you are processing, right? And let's say the context size is 4. So basically we are going to consider previous last 4 words, and you ignore all other words present before that. Same as n-gram language model, right? And then what you do, and this is essentially a CNN types model. So the embedding of the word the will be fed here. This is the embedding of the word the. This is the embedding of students, embedding of opened, embedding of there, right? And this fixed the fixed size window neural network is same as CNN, where you decide the size of the kernel, size of the filter. So here size is the context size. Okay, and then what you do, then you pass it through a linear layer. W is a linear layer, right, which will project all this embeddings to a in a kind of a short squeezed representation, right? From this linear layer you have another linear layer Y, and what this Y layer does, so this is my hidden state, right? And what is this linear layer, by the way? This is a matrix, right? It's a matrix. What's the size of the matrix? Let's say the size of this cumulative embedding vector is m, and you want to get n, so it's called so the size of W would be m cross n. Okay, and then once we look, what is our objective? Our objective is to predict the next word, isn't it? Then what I do, I will pass this embedding through another layer, U. This is again a linear projection, and this U is called unembedding layer. Remember, unembedding layer. And what is the task of this unembedding layer? The task is to project the hidden state to a space where all possible words are present, right? So it will basically project this embedding to a distribution where for every possible word present in the dictionary, I have a probability. Okay, this is also a vector, by the way. It's a vector where every entry corresponds to a word, starting from A to Z, right? Let's say 1 million words are present in the dictionary. Vector size would be 1 million, and every entry will indicate the probability of that word being the next word, right? What's the problem here? The problem here is that we need to decide the window size. 4, 5, 6, we don't know, right? Number 2 is, if we change the window size from, let's say, from 4 to 5, the size of the parameters will increase. By the way, how many parameters are there in this architecture? W and U, right? W is a matrix, Y is also a matrix, U is also a matrix. B1, B2, I mean the bias terms, we'll ignore bias terms for the time. So if you change window size, W will increase. Okay, so therefore, it's not a great way to predict next word. So we need something which is independent of the context size, because if it is context dependent, then W, the matrix size, will increase, will basically vary. We need something which is independent of the context size, and therefore people started using RNN for language modeling, right? And what is RNN? Again, I hope all of you have already gone through the lecture. I'll make it very, very high level. So in RNN, for every word, for every token, right, I have a corresponding hidden state, right? So your inputs are, so this is your input sequence, x1, x2, x3, x4, right? And for every input token, you basically calculate a hidden representation, right? And how do you do that? Let's say H2. H2 is the hidden representation for the corresponding to the word x2. And how do you calculate that? So H2 is a function of x2 and h1. Okay, so the next, so ith hidden states is dependent on I minus 1th hidden state and ith input. And how do you calculate that? So from x2 you basically make a projection. So here is the calculation. So this is my x2, right? And what is e2? E2 is the embedding of x2. So this is my embedding vector, word to vec, right? And what I do here first, I first project it through a linear layer WE. Whenever I say that's a linear layer, you just think about it as a matrix. Okay, you pass it through a linear layer, right? And you get this one, you get this one, WE times ET. You also have the previous hidden state H1. You pass it to another linear layer, which is WH. You get WH times HT minus 1, right? And then you have a bias. And then you add them, and then you basically pass it through a sigmoid. And sigmoid will make sure that it ranges between 0 to 1. So all the entries in the vector in this HT ranges between 0 to 1. What is interesting here is that, so how many parameters are here? WE and WH, right? WH, what is the size of WH? Let's say the hidden state size is 10, let's say. So size of WH will be 10 cross 10. So this will be 10 cross 10, and accordingly WE. Okay. The important point to note here is that you have only one WH which you are going to apply for every hidden state. The same WH will be, the same WH is being applied to H1, to H2, to H3, to H4, and so on and so forth. It is not the case that you have WH1 here or WH2 here. It's not the case, right? Similarly, you have the same linear layer WE, which is being applied to all the inputs. So now you tell me here, okay, so let me just finish the entire architecture first. So you keep on doing this thing, right? And the student, let's say the student opened there, and then in the last word, so let's say here the last word is there, and this is the corresponding hidden state. You pass it through unembedding layer, same way that we did earlier. You project it to a distribution of tokens, right? And you get the next word. How do you get the next word, by the way? So it will just give you the probability of individual token. Then what you do? Either you take the highest one, or you choose, or you sample based on the probability. When you sample based on the probability, it is not necessary that you will always end up choosing the highest one, right? So the first point, so here the parameters are WH, WE, and also U. So now you tell me here, is there any concept of context window? Have we decided, have we fixed the concept of context window? No, right? So you can basically unroll RNN, right, on top of ideally infinite length sentence or sequence, ideally, theoretically, right? What you just need to do, you need to learn these three parameter matrices. But it is not that easy, by the way. Training the model is not that easy. Sometimes we basically assume that this RNN is a sequence model. Why it's a sequence model? Because it basically processes a sequence token by token, right? Whereas if you look at this one, this is not a sequence model. Why? Why this is not a sequence model? Because as soon as we fix the window, everything is same. Then it's a bag of word, right? So RNN is an ideal way of handling next word prediction, because ultimately next word prediction is a sequence leveling problem. The problem with RNN is that it's very slow. Why this is slow? Why this is slow? It is slow because you need to process every token one by one, and to process token n, you have to wait till n-1. You can't do this thing in parallel. You can't process all the tokens in parallel. First problem. The second problem is more of an empirical problem, where we will see that when things are, again, when it comes to long range dependency, right? Let's say you want to predict a word which is dependent on another word which is very, very far from each other, right? Although theoretically RNN should be able to capture everything, all the tokens, right? Because remember, hidden state at nth position is dependent on n-1th position. n-1 is dependent on n-2. So ideally at nth time, you have information of all the n-1 tokens present in the sequence, ideally, right? But in practice, it doesn't happen. Why? We will see later. There is something called vanishing gradient problem, where when we back propagate the loss end to end from your current state to the first state, right? You see that previous few states dependencies would affect less to the loss, right? But before that, let's try to understand how we train RNN, right? So we train RNN in the same way. So for every token, we have a loss, right? And this loss can be a cross entropy loss, right, between the word predicted by the model and the word which should have been predicted, right? So for every token, for every position, we have a loss. This loss is denoted by j. So j1, j2, j3 dot dot dot, right? And then you accumulate the loss. You basically take the sum of all the loss. right? And this loss will be backpropagated. And how do you backpropagate? Backpropagation, RNN backpropagation is difficult. Okay, this is called backpropagation through time, BTT. Okay, again, please go back. I made a very explicit, detailed, presentation last year, right? Please learn BTT, backpropagation through time. Okay, so now if we know how to do BTT, right, we will see that the effect of, let's say, when you take the gradient of this loss with respect to H4, since H4 is dependent on H3 is dependent on H2 and so on, due to chain rule, right, due to chain rule, we will see that each of these components needs to be calculated separately. By the way, what is this? Think about it. H is what? H is a vector. All H's are the vectors, right? So you are basically taking a derivative of a vector with respect to another vector. It's not a simple concept, by the way, right? It will produce a matrix. Okay, and then you see that if the more you move from, let's say, ht to ht minus 1, t minus 2 dot 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 h0, right, the size or the effect of the matrix, the initial matrices to the loss function will be reduced, right? And therefore the initial tokens will not contribute that much to the generation of the next token. Okay, and this is called vanishing gradient problem. The other problem is exploding gradient problem, where the size of this matrix is too large that you will not be able to handle those large matrices, right? I mean, size means the magnitude, right? Not the real size. So although theoretically RNN should be able to capture all the tokens, in practice it doesn't happen. So therefore people thought that let us use some other techniques, and they came up with this concept of gating, right? LSTM and GRU, long short term memory and gated recurrent unit, and both these techniques are RNN, by the way. The underlying mechanism is RNN, but then you have some added components. I'm going very fast, by the way. Okay, so again the assumption is that you already have gone through my previous lectures. So in LSTM, what we do here is that we now define, so in RNN, let me draw something. Okay, so in RNN what we had only one hidden state corresponding to every entry, right? And here in LSTM we define something called a memory. Okay, we define something called a memory. Okay, what is memory? So a memory is again some sort of hidden state, right, which is protected from being accessed from external sources. What do you mean by external sources? You cannot use your input to access to the memory, and this memory is same as our, so you think of this memory as our as our computer memory, and this memory is called cell state. A new state we define, similar to hidden state, a new state we define here is called cell state, and that's my memory. Okay, so for every input xi, I have a cell state ci, or xt, I have a cell state ct, and a hidden state ht, right? And which information, by the way, cell state is also a vector like a hidden state, right? And which information I will basically write to the cell state, which information I will read from the cell state to the hidden state, all these things will be controlled by gates, and these gates are similar to the Boolean gates that we are aware of, right? And or XOR, things like that. But the only difference is that there we just had 0, 1. Here we can have probabilities. Okay, so the gates will control how much information you want to write to cell state, how much information you want to read from cell state, and so on and so forth. And there are 3 gates: forget gate, input gate, and output gate. Forget gate controls what to keep and what to forgotten. Just remember this and then I'll explain. As the name suggests, forget gates, it controls what to keep, what to forgotten. Input gate controls what parts of your cell content are written to the cell. So here I introduce another concept called cell content. What is cell content? Cell content is an intermediate input, as an intermediate processed input that you want to write to your cell state. So so this is called cell content. Cell content is an intermediate processed input that I want to write to the cell, right? So input gate will control how much of my cell content will be written to the cell. And what is output gate? Output gate will control how much of my information from cell state will be read and written to the hidden state. So there are many things happening here. So what are the things happening? Let me again summarize. So you have a cell state, you have hidden state, you have cell content, CC, right? So how much information I will write from cell content to cell state will be determined by input gate. How much information I read from cell state to hidden state is determined by output gate. And how much information I will retain from my previous cell state will be determined by forget gate. And let's look at the equation. By the way, all these gates are again vectors. It's a bit complicated concept, by the way. So if you do not know LSTM, please go back and read. Okay. So this is my cell content, C tilde. C tilde is a function of my previous hidden state, the current input, and I got this intermediate processed input. So what is CT? CT the cell state, my memory. So my memory, whatever information I want to write to the memory, is controlled by forget gate and input gate. So forget gate, you see this gate, this element wise dot product, right? So this is my previous cell state, and the forget gate will determine how much of the previous cell state will come here. So let's say my previous cell state CT minus 1 is 0.8, 0.1, 0.5, and my forget gate FT is, let's say, 1, 0, 0. So if you do element wise dot product between these two, it will result in 0.8, 0, 0. So this part will be moved, this part will be forgotten. Okay. Similarly, my input gate will control how much of my cell content will be written to the cell. Same operation, and then we basically take the sum. So you take some information from the previous memory and some information from your current cell content, and that's going to be your current memory. Once the current memory is ready, then you basically use your output gate to decide how much information you want to read from memory and put it to hidden state. Right? Now, why I said that the cell state is protected from outside? Because if you look at the cell state, the way cell state is being computed, it is not a function of xt. Is it a function of xt? No. Cell state is a function of cell content, and cell content is a function of xt. So you can't access to the memory directly by using xt. Okay, the problem here is that there are too many parameters. How many parameters are there? So for every gate you have parameters. So for forget gate you have WF, UF and bias. For input gate you have WI, UI and bias. We can't train so many parameters. We have limited data. Then in later edition, people came up with the idea of GRU, right? Same idea, GRU is almost same as LSTM, a simplified version of LSTM. So there they said, we don't need any external memory as such. There is no concept of cell state here. And we don't need 3 different gates. We only need 2 gates. One is called update gate, other is called reset gate. And I will use my hidden state as my memory. Okay. So equations are almost the same. Some differences here and there, but in practice, in general, GRU has less parameters than LSTM. But in practice, both LSTM and GRU work kind of similar way. If you look at the accuracy, they are more or less the similar. So the idea is that you start with GRU and then you move to LSTM if you have a lot of data. So there is no thumb rule that GRU is better or LSTM is better in certain cases. No. Okay. Okay. So we moved from Ingram language model to neural language model, where we looked at CNN, RNN, right? And the problems in Ingram language model was that first of all, this long range dependency. Long range dependency is partly addressed in RNN because you still have some idea about all the tokens, right? Some idea. But in statistical language model, Ingram language model, you don't have any idea about tokens which are very far. But the problem in RNN is that you can't. First of all, it's very slow. You can't access all the tokens in parallel, right? And there is another problem, very subtle problem we'll discuss later. So we will discuss in the next class an application of RNN in sequence to sequence problems. For example, machine translation, where you translate one sequence to another sequence. This is summarization, where you summarize one sequence to another sequence, right? So all these things come under sequence to sequence modeling, and we will see how RNNs can be used for sequence to sequence problems, right? Modeling. And then we will discuss in sequence to sequence, we'll see that apart from the fact that RNN can't process all tokens in parallel, there are some other problems. For example, a problem called bottleneck problem. We'll discuss next day, right? So, and then we will see how mechanisms like attention addresses the problem of the bottleneck problem, right? And then we will look at transformer, and we'll see how transformer can process all the tokens in parallel, right? And that would address all the problems that the RNN kind of models have. Okay. All right. Thank you.